surface. So yeah, it's not quite like this. It means here, I think it's easy to get to zero. Yeah, so we've got this thing, such as a cone, and then the dimension forces that way. And you define ER this way, and EZ that way, and M that way. So there's going to be two vectors behind this perpendicular. One of them is E theta, which is into the page, there. And then what do you use as the other one? What else is perpendicular to? Yeah, so it's something in that direction, which is something that has active to the curve, which is it's a plane, it's a plane, so you've got equal direction and that direction. And so what we'll often use for these questions is the direction of the velocity R dot is perpendicular to everything, because you know that it's moving on the curve, then you know that the velocity must be perpendicular to the normal. So you use that statement a lot, and that's where you really get the fact that the force doesn't do any work. It's the fact that it's perpendicular to the velocity is why it doesn't do any work. So, and you had to use that when you were showing that the energy was conserved. But the thing that you always do in these questions is to write down the Newton's second law. So when you get stuck with these questions, that's always the starting point. So you said you've got gravity, and then you've got this normal reaction, so you will always start with that. And then you should usually kind of write down what R is, and you want to decide what unit system to use. In this case, so you've got coordinates, so you're going to do this. R plus Z equals J. And then you give the J there. So the first thing was fine showing that when you get this with E theta, you get 0, because it doesn't matter about these directions, and then the angular momentum is conserved. So that's, yeah, this is the same bit of this, so this is not trivial. That means that we get n dot ER is not 0. Then we get this from this one. But then you say, so you talk here about saying how you're going to equate components in different directions, and that is effectively what you're doing, but you should think of it more as taking a dot product. But taking a dot product is taking a component in these directions, and that's the way that you want to try to think about these things. You always have to differentiate this and then find all the expressions, and I think it's just a good idea to write these down straight away. Because then you can use them all through the question. So this one is R double dot minus R theta dot squared, and then you get 1 over R equals T of R squared theta dot. I just remember that you can write it like that. But these components, which I think is helpful, often to write that out because of that fact that it doesn't mean that this quantity angular momentum is conserved. So that is fine. And to explain why it is conserved, basically, because the thing is smooth, therefore it doesn't do any work, and that's really because it's perpendicular to the velocity. And I think that you both, when you argue that was the case, and then you showed like the differentiators and showed that A is going to get 0. I think that there's a couple of ways you can think about all these problems, because you can either say, I'm going to start by saying energy is conserved, and then I derive my equation from that, or you can say, I'm going to start with Newton's second law, and then I can derive that the energy is conserved, and they're kind of equivalent, and there's always a matter of taste as to which one you say is, or even to say is your starting point. Most of these cases I kind of prefer to say, well, if I started writing down Newton's second law, I should just use that as my, I know it's true, and if you're going to derive anything else, it should come from there. And there's always an easy way to get from Newton's second law to energy. Do you know what that is? And how do you get to say what the energy is from that equation? Well, minus d over R at the end. So it's a conservative force, then there's the gradient of the potential. You've done that there. So let's say that gravity is put on as the gradient of the potential energy. But do you know how I get to that from this equation? There's a kind of a trick. There's not really a trick. But you would multiply by the velocity. That becomes a vector equation. Then you get R double dot dot R dot. There's a lot of dots, and then see the many different things. Minus mg Ez dot R dot, and you have n dot R dot. And the reason that this thing here is the derivative of a half m R dot squared. That's always the case. Does that make sense? Because that R dot squared is R dot dot R dot. And if you differentiate that, then you get 2 R dot R dot R dot dot. So if you remember that you can always write that as quite useful. This, of course, is the kinetic energy. So this is really the rate of change of the kinetic energy is R dot times acceleration. And then this term here, so mg Ez dot R dot is just mg z dot. So you can think of that as d by dt of mg z. So that's the rate of change in potential energy. And in this term we argue for 0. So that's why doing the dot of this with the velocity is a good thing to do, because of the fact that we know that n dot, the velocity, is 0. And often you don't really care what n is. So you can't really limit it, because the whole point is it's just a constraint between us that we're stuck on the cone. So you can always derive the energy like this. So this just tells us that d by dt of half m R dot squared plus mg z is 0. That's the mg is conserved. Which is exactly what you get just backwards. So you can see. But this also would tell you if you had a friction force, so if n was not pointing in the normal direction, then this would tell you what the rate of change of energy is due to that friction force, so that should tell you how quickly you're losing energy. I don't think we ever actually have to deal with friction, but that would come in there. So often with these things you can kind of argue that energy is conserved, but often you don't actually need to do that. You can just derive whether it is or not from the equation. And that's kind of relevant to question 3, because that one you have to do it this way. So so you derived that equation, and that was okay. And then there was this showing at the bottom between two heights. So you managed to show that you get an expression for z dot squared. And then there wasn't quite enough to add this. You did. I think something went wrong there. Yeah. So what were you trying to argue?
I was trying to get. I knew that since I've just got these equations anyway, so I was going to try out quadratic, because that.
Yeah.
That would be.
Yeah, so it can't be quadratic.
Oh, yeah, no, cubic. Yeah, but I'm going to get 3 heights.
It's got to be a cubic. And so it'll be 3 heights, at which what happens?
At which. Z dot is 0.
I mean, z dot is 0, so the three roots of that cubic are places where z dot is 0. And then it didn't work out quite right, but it turns out that one of those heights is negative, and therefore doesn't really make any sense because that's like on the bottom of the cone. So there are 2 places where z dot is 0. And then, so we then just said, it must be the case that it's between those 2 heights. That wasn't kind of completely obvious to me. Why? If I find places where z dot is 0, how do I know that I've just gone to that height and then kept going a bit higher? I could have just, like a stationary point doesn't necessarily mean it's a maximum or a minimum.
So we need to check that.
So you don't need to check that because you, I guess you could check that. You can find out what z dot is. But you don't really want to do that because we have the different formulas again. It's kind of there anyway because you've got this inequality. So you're saying that a cubic has to be greater than or equal to 0. And so I think the easiest way to do that is to draw the graph, because I think this cubic thing is going to look something like this as a function of z. It has one negative root and it has 2 positive roots. So, and this thing here is, I think it's actually z squared, z dot squared, because you have to multiply that as z squared. Somewhere around there's one z squared. But this thing's got to be positive, and so you must have to be in between those 2 places where it's 0. Because you can't possibly go through the 0, because then z dot squared would be negative, which doesn't make any sense. So I think if you draw a little graph, then that's clearer to say that they've got to be between those 2 points. Does that make sense? Yeah. So on this thing, so actually what is it? So one of these things must be right. I guess it's this one. So it was a minus z. So you notice I think that z equals a is a solution of this. And sometimes you can forget that. The fact that z equals a is a solution is clear from the initial condition because you set it off going horizontally with z dot equals 0. And that's quite useful because it's a cubic equation, although they might be difficult to find all the roots. So what was the rest of it? So it was a minus z, and then it's a minus z times 2g, and then plus v squared, 1 minus a squared on z squared. So that's 2g z squared, a minus z, I put the whole thing on top of z squared, plus v squared, z squared minus a squared. This was 2z dot squared. And so that means that 2z squared, z dot squared, is a minus z, trapped out of everything, times 2g z squared. And then if we factor that a minus z, we get minus v squared, a plus z, I think. Does that sound what you're afraid? Yeah, looks like that. And so yeah, this thing is definitely positive, so this thing is always going to be positive. And this is a negative cubic, so it's basically what I've drawn there. And it's got 3 solutions. So z equals a, and the other 2, which are z is equal to, what was it? Yeah, just a funny expression. Yeah, yes. V plus or minus the square root of v squared plus 8 g a. Well, that's just the quadratic formula for the solutions of those. And then one of those, so because that's bigger than v squared, so that's the minus one is definitely negative. So the minus one is definitely that root. And then the other one is a positive root. So the z equals a and z equals that one with the plus sign of those 2 roots. It's not obvious which one's which. That depends on v. So if it can be big enough, this one will be big. Then it can make v small enough, this one will be close to 0. So these 2 roots are those 2 roots. And so that means that when you flip this thing around the circle, depending on how fast you flip it, either it's going to go start very high and go to a higher height and then back down to a, and it's going to do this kind of thing. Or if you flip it slowly enough, a is going to be its highest height and it's going to go down and then come back up again. It's going to do this kind of thing. Yeah, makes sense. And I guess they're the same when the v is equal to g8. V squared is g8. And then when v squared is g8, then those 2 things are the same. So these collide when v squared is equal to ag. What would happen in that case? What would keep the same height? Yeah, so we just go around it. So you've chosen exactly the right speed, so that you can just do circular motion. It doesn't have to go up and down at all. Okay, good. Right, so that's definitely these kind of questions come up a lot in the exams, so it's quite fun. Well, it's not fun. Okay, so then the next question was about this. Yeah, that's fine. The next question was this thing that's going to roll up the sphere. And you just had to come up with some reasonable explanation as to why it rolls up the grid. So it's kind of obvious. Yeah, it's going to start bringing it towards. Yeah, it's one of those things that's really difficult to explain. I mean, it's possible that what they want you to get at here is that conservation of angular momentum again, in the sense that if it starts rolling off down the sphere, it never has any angular momentum, and angular momentum is conserved. So if it starts off with 0 angular momentum, then you can never get any, because there's no forces going around. But it was also fine just to argue that whichever way it goes, it's then going to be confined to that plane. So if you define your x coordinate to be the way that it starts rolling, then you've only ever got any forces in the x direction and the z direction, so y is never going to move anywhere else. And if it's confined to a plane, and a sphere, then it's a great circle. Quite good as a definition. So I don't know, both of you answered that, but that's fine to explain that. And then I want to find these equations. So this book was good. So okay, I thought it was better to try and use vectors rather than using relatively anti-Cartesian components, which kind of works. But usually with these kinds of questions, it's better to try and write things in terms of vectors. And in this case, it's like ER and theta are useful. And part of the reason for that is that the n, you know, n is pointed perpendicular to the sphere. So when you also finish forward to here, you know that the n is going to be going that way. So n, ER, that's fine, ER is going that way. And I think it's said it wanted theta to be that angle. So ER, actually this one's not totally standard with which way the coordinates are, but so ER in this case was going to be sine theta 0 cos theta, and then E theta, when E theta comes this way, it's going to be cos theta 0 minus sine theta, really perpendicular. But I think it's kind of better to work in terms of that, and then you can say that the position of that is R is equal to, actually, because we know it's on the sphere, so just A ER. And then it's kind of slightly nicer, and then you can say, well, R dot A is constant, so that's just A ER dot. And if you do ER dot, you get theta dot E theta. So the technical sign right, because it's not completely, this is not the normal. Normally you have ER going that way and E theta going this way. But also theta's different. So,
if you, regardless of which way you put it, would you always get the same derivatives? So like ER dot goes to E theta.
Yeah, but theta dot. But if I make theta go that way, in this case I've got ER dot is minus theta dot E theta. So I could have defined E theta to be going that way. I mean, it wouldn't really make sense to do that because it would not be in the direction of increasing theta. But you might do that. And it wouldn't go wrong. We just have to keep track of this. I mean, that's one of the reasons why it is a stupid idea sometimes to write these down. Yeah. Just because you can check, so I can do it in my head. If I differentiate that with respect to time, I'm going to get cos theta theta dot, and I'm going to get minus sine theta theta dot. So I know that I get theta dot E theta. But if you're using normal circular coordinates, then you should just remember that. Okay. It's quite straightforward to derive it. And then your R double dot in this case. It's good for that, so you get A theta double dot E theta, and then you get theta E theta dot, which is always going to then be minus theta dot ER. So they give you minus A theta dot squared ER, which is what you've got here. Yeah, it's just written out in more components. But part of the reason why you do that, then your Newton's second law is going to be MR double dot is minus mg, let me call it K this time. So K going that way, plus N. But you know that N is in the ER direction, so you can immediately write it as N ER, straight N ER. Because then when you take components, this is what I'm saying, taking components, you really do dot products. And you can do dot products even if you have not written it all out in your formula coordinate system. So I've written R double dot in terms of E theta and ER, and gravity is written in terms of K. So you might think, well, I need to rewrite K in terms of ER and E theta to be consistent, but you don't really need to do that. You can just say, well, I'm just going to take the dot product, so I come and say, let's take the dot product with E theta, and I'm going to get NA theta dot dot is equal to minus mg, and then I've got K dot E theta, so K dot E theta was sine theta, so this is just mg sine theta, and I have plus n ER dot E theta, that's obviously 0, which is perpendicular. So that gives you that equation, and then you take the ER component and get the other one. So because you have to do the cross multiplying, so we have an idea. So if you've got the coordinates in those, which is useful to doing that, but it makes it easier. But this gives us, minus A theta dot squared is minus mg K dot ER plus n, and that is minus mg cos theta plus n. Right, so that gives you your theta double dot is G over A sine theta. You know that's the equation of the pendulum. With, have you done the pendulum? It's like this, but I'll say that. Yeah, it's basically the same thing. Minus A theta dot squared. So if you only cared about how theta changes, then you wouldn't really worry about this equation, but it always makes sense with n. But if you want to know when you're going to leave the surface, then obviously you need to look at that equation. Right, so and the next part, I think you both said let's use energy conservation. Yeah. So this is again, I kind of think it's a bit, it's almost like you're involved in too many things if you now say I'm going to have energy conservation, because you've already really got that here. So I would prefer to at this point say, well, I've got these two equations, I just need to solve them. Because this one really gives you energy conservation. If you multiply that one by theta dot, it's kind of the same idea. If I take this and multiply by theta dot, then it will give me conservation of energy. Because theta dot is effectively a velocity again. So this gives me d by dt of the half theta dot squared is equal to d by dt of, so it's just the minus entry of the equation, exactly the same thing. And that will always be energy. But the reason why this sometimes is helpful to do is because sometimes you might not be sure whether energy is conserved or not. And this should tell you in a very quick check. Well, it might not be that quick. Sometimes if this equation is more complicated, it might take a long time to make it work. Yeah, I mean, in this case, it's fine to just say, I know energy is conserved because of the thing it's used. But it seems to me, it feels a bit like you're invoking more ingredients than you need. Because you've already really got it here. So this tells us that half theta dot squared plus g over a cos theta is a constant, and we know that when we start at the top, the theta dot is 0, and cos theta is 1, so that's g over a. And then basically you just have to take that and stick it in there. So theta dot squared is 2g over a, 1 minus minus cos theta. And then the cos theta was z over a this time. Then you plug that into there and it tells you what n is. It doesn't tell you how long it's taken. So if you wanted to know how long did it take for it to get to that, then you would need to actually solve this equation, which we have not quite done here. We found the relationship between theta dot and z, but we've not found what theta is as a function of time yet. Right, so and then it fills off when n is 0, or when n bounded goes to. So what happens after that? Yeah, so what kind of path would it follow? And it falls off. Did you do this, or did you do that n2 or 3 or something? I just got it 2 or 0. So we know that it happens at 2/3 of z only. So 2/3 of a, and then we measure from here, so 2/3 of a is kind of it's back here. So it falls off. And then it will fall like that. And this, so which forces are acting on it at that point?
Gravity.
Just gravity. Yeah, so you'll just have mr double dot minus mgk. And so it will follow a parabola. Because the x component of its velocity will stay constant, and the y component, or the z component, will be increasing in time. So in principle, you could kind of work out where it will hit ground by working out what its velocity is. Well, we know what its velocity is when it leaps, because we can work that out from theta dot, it tells us what its velocity is in the theta direction. And then you can carry on to work out what I think the after this is there. But in principle, it's quite straightforward. Once it's not on the circle, then it would be a bit crazy to use circular coordinates. So if you actually wanted to do that, then you have to go back to Cartesian coordinates again and just work in terms of x and z. But if you're writing everything in terms of easy things, that's not so complicated to do. You just switch out between them if you want to.
If the motion is on like an ellipsoid, would you also use cylindrical coordinates?
It's on an ellipsoid.
A similar round object.
That's an interesting question. I might do. Yeah. I guess if ER and theta are not going to be so useful if it's an ellipsoid, because the point of those here is that ER is perpendicular to the surface and theta is tangent. And if the thing is elliptical, then the sort of equivalent of ER and E theta are not going to be perpendicular to the surface. So if you imagine it's kind of like that, and there's a perpendicular direction coming from some origin. So I think that's not going to be very useful. So in that case, we just might better to go Cartesian, yeah. But what we might want to do is write a lot of stuff in terms of the normal and tangent at each point, and you might parameterize those in terms of some theta. I remember you can write the equation of ellipse as like x is equal to a cos theta, y is equal to b sin theta. So we parameterize the surface of the thing in terms of theta. And so it might be useful to use some kind of theta, but then the normal and the tangent dimensions you'd want to write in terms of, well, you have to work out what they are. And then you'd use those to say, well, I'm going to write down, I just write down this. But this is true regardless of what coordinate system we then write on the in terms of. And then we say, let's take the component of that in the normal direction, and that tells what n is, and take the component in the tangent direction. But the normal and the tangent directions are just not going to be given by these formulas, they're going to be given by something else. And they're going to change in a different way in the position. So I think, yeah, I think it would be helpful. So if you're constrained to something, you want to find what's a nice way of parameterizing being on that surface. So if you know that you're on an ellipse, then using some kind of theta is going to be good, because the single variable tells you where you are on it, in the same way that theta here tells us where we are on this great circle. I'm not seeing a question off, but the same idea, I think we tried to do this before with my globe. Oops. What happened to my ball? I had a ball with a big ball. Marble one, 4 off a bit too suddenly. Where do you think whenever we got these people filming us around, the slow motion? It doesn't look like it falls off after 2/3 of height. Try and catch it. Yeah, I think it's I was quite surprised that it's 2/3 the way up. But the one thing that I did think was, so if you account for friction, and I think you can argue that it must be a bit further down. Can you see why I can say that?
It's going to lose some of its energy, so it'll have less energy in the horizontal direction.
So what do you mean by energy in the horizontal direction?
It'll have less velocity in the horizontal direction, so it's the same problem.
I think that's sort of true, but why does that mean it goes down for longer? Because it's also going to have less energy, it's going to have less velocity in all directions. Because it's not going to have that way.
It's accelerating due to gravity in the vertical direction, but it's going to be decelerating mainly.
Yeah.
Horizontal direction.
I think that's kind of true. So where would the friction force come into anything that we write down here? Anything there? Yeah, so I have another force which is in the E theta direction. Yeah. Obviously, it's a frictional force. And so what difference would it make to this bit?